This meeting being
Yes, hello everyone. Today we have a very exciting speaker, Shantanu Nene. He recently completed his undergraduate studies from the IIT Bombay, and he has attended IMOTC multiple times. So he'll be talking about the probabilistic method. So super excited to hear it.
Yeah. Okay. So before I start, how much did you guys go through the expected value section of Rushel's book, or maybe like his lecture? Something.
Does the Otis global unit work?
What like do you have like a basic idea of expectation, random variable expectation?
Yeah, sure.
yeah.
Linearity of expectation. Acha. Also, maybe I'll still go through this one, but have you guys seen like basic applications of probabilistic method? So, for instance, for this RNN.
Not by
No.
name.
Okay, fine. I'll do this
No.
one.
What is
I'll start
RFNN?
Okay. Wait, how do I? Hang on. So we start off with like generally my end goal of this lecture is to prove something called like in extremal graph theory called the forbidden subgraph problem. So I want to get some non-trivial results in that. And most of our lectures, most of the examples I'll give are in that direction only. So I'll first introduce the problem. So it's a generalization of Turan's theorem in some way. So do you guys know Turan's theorem?
No.
No.
You guys know Mantel's theorem?
Yes.
Okay.
Some people don't know
Fine.
Mantel.
So the basic idea is that this number x n comma g, that is the max number of edges in an n vertex graph without a copy of g. So the classical problem is what's the maximum number of vertices in a triangle free graph. So if you have n vertices and the graph is triangle free, then what's the maximum number of vertices that you can what's the maximum number of edges
N square by 4, right?
Right. So
And
for instance, like what Mantel's theorem says is that x n and triangle is this n square by 4 floor. So it says the maximum number of edges you can put in an n vertex graph.
how do you prove that? Though I got the case, I got how you get n square by 4, but how do you prove its maximum?
I think you do some double counting. I don't remember. There are like many proofs of this.
I think Kazi Aryan's INMOTC combinatorics handout has it as an example. So I can put that in the chat.
Yeah. You should do that. So if you can find, I'll tell, this is called Mantel's theorem, but there is something called Turan's theorem, which is a generalization of that. And I don't remember the exact, so this can be calculated exactly. So you guys know what KR is? KR is the complete subgraph on R vertices.
Clique, I guess.
Yeah, click on R vertices. So it's instead of triangle, if it's KR free, what's the maximum number of edges you can have? And I don't exactly remember the exact. This can be calculated exactly, but for our purposes, this much is enough. So the maximum number of edges you can put in an n vertex graph, so that it's KR free, is roughly like R minus 2 by 2 R minus 1 n square. Right?
Is that O1?
A small O1. So this is small O.
How small? Is it like 10-ish?
No, small O is
the
our
small
notation.
O. This small O ones means that this quantity goes to 0 as n goes to infinity. It's some quantity that is sublinear. Yeah, it's like goes to 0 basically.
It's not constant.
It's not constant. It's not capital O. It's small O. So capital O would mean constant, capital O1 would mean constant, and I'll like abstract this further and say this is now capital O n square. This is Turan sum, and in fact, like this quantity here, x n k r, can be explicitly determined. It's like, and you can find like the maximal cases. There's something called a Turan graph, which is where, for example, in the triangle-free case, the maximal case occurs when it's complete bipartite. The Turan graph, it's complete multi-bipartite. But again,
Okay,
this
so this gives the maximum number of edges in the n vertex graph, which is KR.
without containing KR. Yeah. If a graph has more than these edges, it will contain KR. And there's a very strong generalization of this called the Erdogan theorem. And that says that actually gives the answer for most of the graphs is where chi g here is the chromatic number of G. So what's the minimum number of colors needed to color?
This is big O or lower?
No, this is same, small O. Big O, I'll write very big, so that this is smaller. It's a generalization of that because the chromatic number of the complete graph is R, right? And as a consequence, so this basically solves the problem as long as the graph is not bipartite. So if G is not bipartite, this first term is positive. 1 minus 1 upon, it's at least half in fact. So up to the leading term, at least x and G is known if G is not bipartite. And as a consequence, if G is bipartite, then x and G is small o of n square. This is small o. It's small o of 1 times n square, so it is small o of n square. If G is bipartite. So small of n square is very vague to say. Like here you can say it's big O of n square, but you know the constant at least. What does small of n square mean? It could be like constant, it could be log n, it could be linear. What's the exact rate of growth of x and G when G is bipartite? That is unknown, and that's a very hard problem to solve. It's still unsolved to some extent, but we have very good upper bounds. We have decent. We have very bad lower bounds. We are getting there. So this will be.
Yeah. So like this, what do you mean by G here? Like this says in a vertex of in an n vertex graph, it is what free?
G free. So there's no copy of G. So G could be like KST, for instance. Complete bipartite graph. So what is the minimum number of edges? What's the maximum number of edges you can put in an n vertex graph? After which it will contain a KST, or it will contain like this graph. Let's say
it will contain any complete or bipartite.
Any graph. Like this graph could be something else, but contain any graph isomorphic to G basically. Right.
When we say that a graph does not contain just a, like if we just put G as a single vertex, then what does it mean in this case? How do we define X?
Then it's like, okay, I guess you need at least one edge. Otherwise, every graph will contain zero. Not even zero, it's like not defined.
So we leave it as undefined, not zero.
I mean, I guess you need at least one edge.
I mean, if chi of G is 1, then does it really matter what the result says?
Okay. This is like undefined then.
Wait, how do you even have chi of G1? It's just one vertex.
If it's like completely disconnected, like there is isolated vertices.
Just take like 0 edges.
Yeah, like one vertex, right?
Any number of vertices.
Okay, so this will be our end goal, but before that, I'll build up the required tools to get there. And first is, there are like, I would say 2 principles. The first principle is, don't think, choose randomly. This is due to, he didn't say this exactly, but he was the one who pioneered this. If things get too complicated, just you don't have to think, just choose things randomly. And this method works wonders in unexpected places. So to that extent, I'll share one example, which is RNN. So you must have known the classic problem. If you have 6 people, each pair is either friends or enemies. Prove that there exists a triangle of friends or a triangle of enemies. Right?
Yeah.
So RNN is a generalization of that. Key, it's the minimum number of vertices n such that if edges of Kn are colored in 2 colors, then there exists monocolored Kn. So what it says is that, what's the minimum number of vertices? So that if you take a complete bipartite, complete graph on those vertices and you color the edges in one of 2 colors, then there'll be like a Kn in either red with all edges red or Kn with all edges blue. So for instance, R336, that's the classic thing. And it's like known R44, I think is 21. I think R55
like,
or
can the arguments be different also, like R34?
yeah, R34 is possible. So R3 actually I should say that R34 will be ki, it's either red K3 or blue K4. So in fact it's RST is better. So RST is like either red KS or
Okay.
if the 2 colors are red and blue, it's a red KS or blue KT. So either the graph contains a red KS or a blue KT. And well, first of all, it's not even clear if RST exists. Like what if there are arbitrarily large graphs without red KS or blue KT? And this is
Similarly, we can't really say that RNN exists, right?
yeah, we can't say RNN exists.
At least
but
not right now.
not right now. But there is like a very easy-ish bound to get. Let me just check it. It's like R
2 to the n
ST.
r squared, no? We can't just have 2 to the s plus t squared.
I think this is, you can take this as an exercise. Prove that RST is less than or equal to RST minus, let me just check that. Sure, this is correct. Yeah, prove this later. This is not probabilistic. This is just some induction argument. You have to prove RST less than or equal to RST minus 1 and RS minus 1t. And you know some small values of, you know, R2 anything. Like R2, 2, you know that. So that's like 1. Because if it has one edge, it has a monocolored K2. So starting from that, you can construct maybe R2, 3 you need. But if you know these things, then inductively you can prove that RST is indeed finite. So it exists for all S and T. And not only that, you get a decent upper bound. This is just follows from this looking like a Pascal's triangle situation. I think you get a upper bound of this form. Yeah.
It should be S minus 1, I think.
No, S minus 1, sorry.
Yeah, it needs to be symmetric.
Yeah. You get RST is S plus T minus 2, S minus 1. And so you get an upper bound for RNN. And that is like 2n minus 2, choose n minus 1. And if you know Stirling's approximation, if you don't know, that's like this type of upper bound, 4 raised to n by root n. So you get an exponential upper bound on RNN. And for a long time before Erdős, the best lower bound was like n square by 2. Sorry, n cube. It was not that bad, I guess. Best lower bound was of the form n cube by 6. Right? So you have got an upper bound, which is just from easy counting, 4 raised to n by root n. And there was a lower bound, which was from an explicit construction. So someone had constructed a graph with n cube by 6 vertices, colored its edges in 2 colors, so that a monocolored copy of Kn did not exist. And for a lot of while, we're stuck on this, like this polynomial lower bound. It's pretty bad. Until Erdős proved the following. So that's a massive improvement over n cube. So n cube by 6, you go to exponential level lower bounds, 2 raised to n by 2. And while this is still, I think, at least the exponent, so this is like root 2 raised to n. Root 2 has not been improved yet so far. There are other things that have been improved. We will see one of the improvements today. But at least the exponent has not been improved. So we have an upper bound of like 4 raised to n, lower bound of root 2 raised to n. But still is much better than n cube over 6.
We have not lowered the upper bound.
I don't think so, no. Again, the exponent has not been lowered. I don't know about the constant, but at least the exponent is still the same.
So ideally, if we'd want to prove this strengthening, we'd have to consider a graph on 2 to the n by 2 ceiling vertices or floor vertices, I think. And then we need to show that there exists a graph such that like there's no monochromatic Kn.
Yes. You need to. We'll like choose an m greater than 2 raised to n by 2, and we'll consider Km, and we'll find a coloring of the 2 edges of Km in 2 colors, so that there is no monochromatic K. That's the plan. Right? This m is like ceiling of this plus 1, something like that.
Okay.
Exact numbers won't matter that much. Just show it's greater than 2 raised to n by 2. But let's start from this now. You have got a Km, and somehow you have to color its edges in 2 colors so that there is no monochromatic Kn. How do you do that? Well, we apply idea 1. Don't think, choose randomly. Okay. So we won't think. So every edge can either be red or blue. So we just randomly color it either red or blue with equal probability. So why do we choose half?
Symmetry maybe?
Because
I don't see why it should matter, but symmetry.
if it was not RNN, if it was RST or something, do you think half would be optimal?
Okay, right. It might shift.
In this case, it's RNN, so like it doesn't matter if it's red or blue. You just don't need a monochromatic gain.
So if it were RST, we would say probability something, and then we'd calculate the something which is best for us.
Yes, that.
Like we will be biased towards the larger one, right? Like if we have RST, we would be biased towards the larger one because we are looking for like a thing.
Yes. If like T is greater than S, then we'll color a edge blue with higher probability, higher than half.
Yes.
But okay. But this will ease our calculations since we are only doing RNN. So now. There's no monochromatic gain. This is what you want. So there are events where the entire graph is monochromatic. So what we want is what is this probability? And if this probability we are done. Why?
Because then there exists something. Like if there didn't exist something, then probability would be 0.
Yes. So if there was no such coloring, the probability is 0. But as long as the above probability is greater than 0, we are done. So instead of considering this exact probability, we look at probability that there exists a monochromatic gain. And I'll rewrite this probability as a union of events. So union S subset Vg mod S equal to n. S is monochromatic. Right. So what's the probability that there's a monochromatic gain? It's a probability union of the event that S is monochromatic, and where S is a subset of Vg of size n. I will use the first basic bound from probability, which is called the union bound. This is like very important bound. Have you seen the union bound before?
No.
No.
Okay. So what it basically says is digression. Probability of A union B is less than or equal to probability of A plus probability of B.
Okay. That seems
So like
simple.
yeah, with A union B will have some intersections. So probability of this would certainly be less than probability of this. That's what I've used. So I've written this event. There exists a monochromatic gain as a union of various.
I think that is just a formula, right? P of A
Yes.
equals.
Yeah. So this is equal, and since it's a union, you can take the union out and you get an inequality. So the union bound gives us that union over S in Vg mod S equal to n, that probability that S is monochromatic. Now we just need to focus on this. So you are given some subset S of Vg of size n, and we want to know what's the probability that S is monochromatic. So tell me, what's the probability that S is monochromatic? S is like subset of Vg. Mod S is n.
1 by 2 to the n minus 1, right?
1 by
2 to the n minus 1.
well. Okay, maybe I should not use S is monochromatic, but a subgraph induced by S is monochromatic, where we are coloring the edges.
Okay, right. Then like there's going to be 2 configurations where it's monochromatic, and the total number of configurations should be 2 to the n choose 2.
Yes.
So
what's
then
the
2 by 2
probability?
to the n choose 2.
Correct. So yeah, it's either red or blue. What's the probability that all edges are red? 2 to the n choose 2, because there are n choose 2 edges between them. And what's the probability that it's blue? 2 to the n choose 2. So it's 2 over 2 to the n choose 2. We'll put this back here. And how many subsets of Vg are there with size n? That's just m choose n. So that means probability that there exists a monochromatic gain is less than or equal to 2 m choose n 2 raised to n choose 2. And we want this
to be less than 1.
Yes, to be less than 1. Because this is the complement of the other event that we are looking at. There exists no monochromatic gain. So if we want this event to be greater than 0, we want this event to be less than 1. And how do we guarantee that? We make this quantity less than 1. So we want like 2 raised to m choose n less than 2 raised to n choose 2. Right. And solve above. Now it's just a bit of calculation to get like m is you need m to be, this works basically. I'm not going to do that. So if you put m equal to 2 raised to n by 2 here, then this quantity is less than, but this is approximately, if I just do a rough calculation, this is some 2 m raised to n by n factorial type. And this is approximately 2 raised to n square by 2 types. So some n factorial term here comes. If it's like 2 raised to n by 2, if I put here, then the 2 raised to n square by 2 term gets cancelled and you get left with 2 by n factorial, which is less than 1. So back of hand calculation, it's not exact, but that works. So now we are done. Why? Because if we choose m approximately 2 raised to n by 2, slightly more than 2 raised to n by 2, and we do all this calculation again, what we would have proved is that the probability that there exists no monochromatic kn is greater than 0. Right? So that means there exists a configuration, there exists a coloring for which there is no monochromatic kn.
Wait, could you like tell the thing how we got 2 over 2 n choose 2?
So this is a technique we use a lot, which is called back of the hand calculations. You have to be more precise. I have not been exactly precise after this.
No,
step.
not this.
Oh.
I was talking about like how you got that the probability is 2 over 2 raised to the power n choose 2.
Oh, this one.
Yes.
So you have got S has n vertices, so the number of edges in S is n choose 2.
Yeah.
So and we are coloring each with probability half. So what's the probability that all the edges get colored red? Let's say.
Like
Will be
1
half times half
okay.
times half.
Yeah.
Oh, right. I have to be slightly more carefully while I'm saying something. Probability half independently. So every edge, you don't care about how the other edges are colored. For every edge, you are flipping a coin. And that's why you can multiply the probabilities here. That's why I can say, oh, if you have n choose 2 edges, the probability is 1 by 2 raised to n choose 2. Right?
Yeah.
Did you get it?
So I wanted this probabilistic bound to be like, it feels like it should give a value on the same order as actual answer, right? Because of how probabilities grow down very quickly, right?
So actually, that's like
So
that was my next point. So if you do this calculation, actually, if you take m is 2 raised to n by 2, I'll tell you why 2 raised to n by 2 is a bad lower bound. That will bring us to my second point and the second tool that we are going to use it. So I claim that 2 raised to n by 2 is bad. Why? So let's put m is 2 raised to n by 2 here, and remember we got this upper bound. So I'll be using this upper bound as well. So you'll get something 2 to the n by 2, choose n over. I'll just use n square by 2. And remember we had calculated this is approximately some 2 by n factorial. Maybe there are some other bounds. Maybe I should write like n raised to 1000 by n factorial. Just considering every bad bound, very bad bound, but. And what we had said is if n is large, in this case, if n is anything, this is less than 1. And so the idea is that if n goes to infinity, this goes to 0, right? And what that means is that if n is very large, if n is very large, then if you color km randomly, so you just color it randomly, then there's a very high probability that there is no kn. Right. But we are saying that m is so small that like for most of the colorings of km, there is no kn. Yeah. So in fact, we're saying something stronger with this km. If n is very large, then this goes to 0. And like 99% of the colorings will have no kn.
But this is a better bound than
So
this is a better bound on the upper bound, right? I mean, this bound, like if I double this, I believe that it should go to closer to 100%. But that thing is to do the n times this much. So I'm pretty sure the actual value is closer to the lower bound in this case.
Not really. Like you're just saying, you have got this 2 to the n by 2, and if you take m is 2 to the n by 2 and you color it randomly, there's a 99.99% chance that you'll get no kn. That's what you're saying. And what you want in the maximum is there exists one coloring. So you don't want 99% of the colorings to have no kn. You just want one coloring to have no kn. Right? Here for this 2 to the n by 2, you're getting the 99% of the colorings of no kn. What would I do with these many colorings? You just need one kn. So that's why this m is like not a good bound. And how do you improve this? That whenever we are dealing with probabilities, won't such a thing always happen? When you are dealing with some beyond probability less than 1. How do we make it less than 1 without making it too small? That's like very hard to do, and I don't know the answer. Like, there's no direct way to do anything. So maybe Erdős's paradigm here, it says, where did it go? What? Where did I write it? Don't think, choose randomly. That is not the best for most of them. That will give you a decent bounds for a lot of cases. But what that would make you is that will make the bound true in most cases eventually. So like 99% of the colorings would have no kn. We don't really want that. We want just one coloring to have no kn. So maybe we'll have to think a little. So let's think a little. We come back to this same problem, and I'll tell you how to improve this bound little bit. Like, you won't be able to improve the exponent, but you'll improve the factor. So instead of like 2 raised to n by 2, I'll now prove that Rnn is greater than something like this. Right. This is a better than other one because you have an n by e factor here. So it's like 2 raised to n by 2 times something linear.
Essentially, like, what do you exactly tell us the difference between big O and small O?
Small o of something fn, like upon fn goes to 0 as n goes to infinity. And big O of fn just means ki like it's less than or equal to some constant times fn. Here it's small o. Whenever I like 1 plus O of 1, it's generally small o, because if I wanted to write big O of 1 anyway, why would I include the 1 at the beginning?
Okay, so like O of 1 does not have a specific value, right?
No, it's not a specific. It just says ki, oh, if I take Rnn minus this quantity divided by this quantity, that will go to 0.
Does O1 times n by e into 2 to n by 2 go to 0? In this
No,
case?
that will, so O1 times something fn upon fn goes to 0.
Yes, but is it possible O1 times fn also goes to 0?
It's possible. I mean,
In this case, does it go to 0?
this case I don't know. I don't think so. I don't think it goes to 0. At least the bounds that we get, it does not go to 0. Okay, maybe I should write this as, I'm writing this as plus now. I think writing this as minus is slightly better. Because why would I get a plus for the bound? It's more of this form. Generally, it's sort of misleading. Whereas small o, this is not saying anything whether this is positive or negative. This is like some constant, but small o just means that quantity goes to 0. So it could either be positive, either be negative. Or maybe writing this in this way is better. It's not, the bound is not exactly n by e into 2 raised to n by 2. There is some error term, but that error term is small. Like, it goes to 0 in comparison to the main term.
Okay, so like O of f of n by f of n goes to 0 as n goes to infinity, and big O of f of n by f of n is just a constant. Just goes to
It's bounded. It's bounded basically.
It's bounded.
It's bounded by some constant. And big O, generally when we use big O of f of n, that means that the quantity is positive and f is also positive. But when you use small o of f of n, it's can be both. Slight abuse of notation, I think, but yeah, here it's small o, and I'll write it as minus. I think that will be better. So how do we prove this quantity? Like just randomly choosing something is clearly not working. It will only give you 2 raised to n by 2. It won't give you anything better. So what we do is, let's say you again choose some m. So you again have m, and the color came into color same as before. Randomly your color. Now instead of asking what's the probability that there is no kn, we'll ask you how many kns are there. What is the expected number of kn? And this quantity can be calculated exactly using linearity of
Linearity. Linearity.
Right. So I'll just write this because number of kn would be like for each set there is some probability that it is monochromatic. Number of monochromatic kn. So if I just write it as like this, bg. I'm writing this as gs. Like this is the subgraph induced by s. Subgraph induced by s. And this is sum of probability that gs is mono and over all possible subset of vg of size n. This follows from linearity of expectation. If you, I can give like slightly expanded version of this. This is like summation where 1 is the indicator variable. So 1 will be 1 when gs is mono, and again the s vg. So 1 will be 1 when gs is mono, and it would be 0 when gs is bichromatic. And on this expression, we are using linearity of expectation. That's how we can expand this expectation as a sum of probabilities, because expectation of like one given event A is just probability of A. Is this part clear?
Yes.
Yes.
So we're just expanding the expectation. And again, what's the probability that GS is monochromatic? We had calculated it above. It's this 2 raised to n 2 by n choose 2. And number of S is again we had calculated above. So all in all, we get that expected number of monochromatic gain is m choose n. Something like this, right? Now,
So this is the exact thing.
this is the exact thing. Yes, this is the exact thing because linearity is exact. There's no inequality here. It's exactly equal to this. So now we think instead of making this like less than 1.
One thing.
Huh?
Aren't they what you say not independent? If we have one clique is monochromatic, then it increases the likelihood of another clique being monochromatic.
But this is not linearity
independent.
of expectation does not require the events to be independent. That's the power of it.
Yes.
It will work for anything. E of x plus y is E of x plus E of y, regardless of whatever x and y are. They might be completely opposite of each other. They might be the same thing. Doesn't matter. It's still always linear. So now we have this quantity. What do we do with it? Well, instead of making this small, what if we just remove one vertex from each monochromatic gain? So what we do is we randomly color km in 2 colors. get approximately these many kns, and we remove one. So I'll call this quantity something. I'll call this small k. And then we remove one vertex each from every monochromatic kn. Right? So number of vertices left will be, started with m vertices and remove k1, m minus k. But this graph would have no monochromatic kns. Why? Because we have removed one vertex from each of them, right? So there can't be any left. Now all we have to do is estimate how many vertices are left, right? We have no, like, the probability that there is no kn is like 1 right now. So the randomness in the number of kns left is gone. All the randomness exists is how many vertices have been deleted, right? So what's the expected number of vertices left? Okay, maybe I should make this k instead of, it's not k. This is k. Number of monochromatic kn is k. So what's the expected number of vertices left? Well, m is constant, so m minus expectation of k, which is m minus this quantity.
It will be m minus n time expectation of k.
No, we are removing one vertex. That is enough
Okay.
to destroy that kn. Like, you don't need to remove the entire kn.
Okay.
Right? And well, sorry, 2 raised to, right? And if we can make this bigger than this quantity, if we can make the m minus k bigger than this quantity, in expectation, will be done. Because if expected value of some quantity is bigger than 100, then that quantity attains a number bigger than 100 at some point. Otherwise, the expectation will be less than 100. If this is bigger than required, we are done. Again, I won't go into the calculations now, but let's just say we set this quantity be n by 2, and so this will get is equal to m by 2. And solving this, gives m is, this uses some Stirling's approximation, so I'm not going to do too much detail. But what we do is we want this to be like large, so we just set this to be like m by 2, and as long as m is large, we'll be done. And yeah, actually you get m by 2 is this. So because the number of vertices left is m by 2, so the number that we want is actually m by 2. Solving this give this quantity. Exercises to do, solve this yourself. That is fine. But what we learned here is the second main step, which is alteration. And this is by, I don't know, someone. But Erdos was early 1940s. This appeared a few years later, I think 50 or 60 somewhere. And basically, probability will not give you the entire picture. You would still need to tinker it a little bit to get the exact answer. And that's what we did, kind of like, we have like lots of kns. How do we, it's still not very deep. Like, it's still, you just remove one vertex from each kn to get rid of all the kns. That's all we did. And we ended up with this quantity. Now we have enough tools. We need one more thing that's not exactly a tool, so I won't go into it too much. But now we can tackle the problem of is how much. All we know is from the above, like Erdo-Stone theorem, that it's small o of n square, but that's not very exact. And well, again, this I'll leave as an exercise to you guys. There's a very relatively easy upper bound that you can get on this. Let me just check the exact form. Capital O of n raised to 2 minus. So this is a more concrete. You still don't have the constant. The exact constant can also be like there is a proof that gives you the constant as well, but it tells you that the exponent instead of n square is something slightly smaller. It's n raised to 2 minus 1 by s. If s is less than or equal to 2. So it's a pretty good upper bound on this. And the proof, which I'll leave as an exercise, is by double counting. How? Well, the number of like K1Ts, I think, to calculate is like and yeah, and then you need like s of them to have the same value. Okay, I won't go into the details too much, but this is the starting point. The number of K1Ts in the graph is the summation of degree we choose T. Like you can just choose T of them. And if you want KST, you need S of them to have the same. So basically you get that the number of KST is less than or equal to something. Yeah, and we not n choose. And this you have to make less than 1, and that gives you some bound of this form, like O(n) raised to 2 minus 1 by s. And the reason I'm not going into the proof is we'll prove something stronger than this. So we have got this again. If you want, again, here the problem with the lower bound. So the previous problem we had looked at a lower bound on RNN, and the upper bound was leagues away, and it was very hard to, very easy to prove the upper bound, very hard to prove the lower bound. In this case, the upper bound is straightforward. Like it's not very hard. It's just simple double counting. The lower bound is very hard. Like it's beyond the scope of undergraduate courses, right? Like a lot of the constructions for the lower bound require like algebraic geometry, Langevin bounds, and all that, projective geometry. And yeah, there is randomness does not give a very good lower bound. And again, this we don't know the exact lower bound for this. This exact lower bound has only been found out in some cases.
What do you mean exact lower bound?
So this is an upper bound, like O(n) raised to 2 minus 1 by s. What's the lower bound? Like what's the sigma? Like is it sigma n raised to 2 minus 1 by s? So essentially that if you have n raised to 2 minus 1 by s edges, then the graph contains an KST, is what this is saying. But then what's the maximum number of edges you can have without containing KST? Can you have at least n raised to 2 minus 1 by s edges up to some constant without containing a KST? That's not known. It's only known if like T is much bigger than S or something. But if S and T are comparable, then it's not really known. But it's fine. So Now what we'll do is instead of looking at KST, we'll just look at H, which is some A union B, comma E, let's say, is bipartite. Okay, we'll only be focusing on bipartite graphs, but not necessarily complete bipartite. And we want to give an upper bound for X and G, X and H. And well, let's find some algebraic key. Mod A is A and mod B is B. So to find an upper bound on X and H, let's assume you have some amount of edges left. How would we try to find H inside this graph? So you have this graph, like edges, something like this. How do we, like, we want to find an H in this graph? We don't know what edges are there. We just know that there is a sufficient amount of edges there. But suppose we try to embed A first. So what we do is we find some A naught. Suppose this is the graph G. We find some A naught which is subset of G. Then mod A naught is A. And that we declare that set as A. So suppose we have found A here. Suppose this is A naught. And now what we do is we try to add like vertices to B. So suppose we have got A naught, we try to add this to B. We try to add this to B, because this is not a good. Try to add this to B, one at a time. And you've got this A naught here. And suppose you have added like V1, V2, Vi minus 1 to B. B is still not constructed yet. This is our B naught so far. And we want to say, oh, there exists a Vi equivalent. So here I is B. And we want to add a Vi to this set as well. We have already embedded A. We are embedding B one by one. And Vi in the original graph has some edges here. Right? Let's say it has R edges. Then what we want is that, well, like the corresponding vertices. So you have this Vi and you have this R many vertices here. The set of these vertices should have a common neighbor. And not just that, that common neighbor has to be different from, well, V1, V2, Vi minus 1. And it has to be different from A naught. Okay. Let me rephrase this in some easier way. You have got A naught. We have already embedded A naught. When can we find a vertex B1 that corresponds to, suppose B is this, V1, V2, VB. And we have found it A naught. When can we find a V1? Well, if V1 has these three as neighbors, then three of these three vertices in A naught should have a common neighbor that's not in A naught. If they have that, then we can find V1. So we have found V1 and we start our B naught journey. Look at V2. Again, suppose V2 is adjacent to these two vertices. Then these two vertices should have a common neighbor. That neighbor should not be in A naught and that neighbor cannot be V1. So they should have a common neighbor, not in A naught, and that is not V1. Right? So now we'll use some very loose bounds. That suppose max degree of B is R. Every Vi only has R neighbors. And suppose every R size right? what is this saying? Ki every R size subset of A0 here has at least A plus B common neighbors. So it does not have one or two, it has many common neighbors. Then we claim that we can embed H. Why is that? Well, we follow this process again, that you have got A0. We try to embed V1, let's say. We look at the set of neighbors of V1. That is a subset of size at most R. That has at least A plus B common neighbors from this. So it must have a common neighbor that's outside of A0. Otherwise, it will have at most A common neighbors. So we can find such a neighbor V1, and we have found our V1. We have started our B0. Now to find V2, again we look at its neighbor set that has size at most R. And again it has A plus B common neighbors. So if the set of common neighbors were all in A0 or it was all in V1, let's say, that will only have some A plus 1 common neighbors. But it has A plus B, and B is at least 2. So there is some common neighbor that's not in A0 and it's not V1. And that we can make it as V2. Similarly, we can find V3 and so on to VB. But again, if once we are finding VB, we already have an A plus B minus 1 size graph that we have constructed. We look at the neighbors of VB. We look at their common neighbors of this group, suppose so neighbors of VB. We look at the common neighbors of NVB. And NVB has at least A plus B common neighbors. But so far, we only have A plus B minus 1 vertices. So there exists a vertex common neighbor that's outside of these two sets. Should I repeat this?
Wait, could you just tell the definition again? Like what was H? Like the first part I missed.
X and H is like what's the maximum number of edges you can put so that there is no H embedded in it. Like you want to find,
Yeah, A and B. A and B. I was asking A and
oh,
B.
A and B are just two parts of H, and we want to.
H is bipartite.
H is bipartite. Yeah. H has two parts, A and B. We want to embed both A and B in G. What we do is we start off with some A0 with size A, and we embed B one by one. So we embed V1 by looking at the common neighbors of NV1. So we look at the common neighbor of NV1. If there is a common neighbor, we make it V1.
Yeah, got it.
Right. And that's why this bound is important. If every subset has A plus B common neighbors, that means we can always find a common neighbor that's outside of these constraints, like outside of A0, outside of V0, so on. So that's how. So if these two properties are satisfied, if max degree of B is R, and suppose every R size, we can find an A0 of size A. Again, A0 has size A, and every R size subset of A0 has at least A plus B common neighbors. Then we can embed H in this. And this was a very recent theorem, which by Alon, two other guys.
Alon isn't the combo null guy?
Combo null guy. Alon Krivelevich and Sudakov. Sudakov has other theorem. This is 2003, so very recent theorem. That if H is bipartite, just 1 second. And every vertex of B has degree at most R, then X N H is O H n raised to 2 minus 1 by R. Here OH means that a constant will depend on H. So the constant depends on A, B, the structure of H, but it does not depend on small n. And this is a generalization of the bound that we had here. Why? Because in this case, trivially, every vertex in the T size part has degree at most S, because there are only S vertices in the first part. So this property is satisfied when, like, for the complete bipartite graph, and that gives the above bound. Like, I think it's called some Zarankovich bound or something. It's very hard, but doesn't matter because Alon has a better bound for us. And how do we prove this? Well, all we have to do is find an A0.
What does big O H mean?
Here, big OH means that the constant here, that this just means there's some constant times n raised to 2 minus 1 by r, right? The constant
Yes.
depends on H, but does not
And
depend
how
on
and how does it depend on H? Like
the
what order?
constant of. Huh?
What order is it on H? Like
What
is
do you
it
mean
H
order?
squared?
H is a graph.
H is a graph.
Yeah, but like H ka number of vertices I'm assuming, right? I'm saying
That I don't know.
like if I say
Some-
the H is a graph of A, but A comma B vertices and C edges, how is it dependent on C H?
I am not sure. Let me. I think it's like actually we can find the constantly will pop out of the proof, so you get an explicit one. It's a pretty okay. It's kind of weird constant. But okay, it will pop out. It depends on A, B, and R in some way, but you'll see. Anyway, to finish the proof, all we have to do is find an A0. Which A0? Well, I'll write both of these things down. Mod A0 is A, and every R size subset if we can find such an A0, we'll be done by our above argument. We can then embed B0 one by one. Now, how do we find such an A0? This is like where the brilliance. So, if it was just until this point, even Erdos could have done this. But the next step is where Alon's brilliance. Okay, I'm giving too much credit to Alon. Maybe the other guys also thought of it, but it's where like their brilliance comes in. We don't choose A0 directly. So the dumb thing to do is to just choose a random A size subset of the vertex set, right? But we don't choose A0. What we want is a very special property of A0 is that A0 should have a lot of common neighbors. So what we do is we choose some T in some way, like somewhat random subset. I'll tell you how to choose the later, and let so n of t is the common neighbors of t. So instead of choosing A0 directly, what we are doing is we are choosing a T and we are just letting A0 be the common neighbor of it. Again, here, instead of equal to A, even if we get greater than equal to A, it's still fine because we'll just take a random A size subset of A0 and do the same thing. So instead of choosing A0 directly, we are choosing it in this weird way where it's like number of common neighbors. What this allows us is like, it allows us control on the neighbors of A0. Otherwise, we have like no real control. Like this is a very weird and strong condition to hold. Like R size subset of A naught has a lot of common neighbors. Here we are saying if we know the common neighbors here, A naught has every element of A naught has all of T as their neighbor. So yeah, there's a lot of common neighbors here. And well, firstly we'll calculate what the expected size of A naught is. Again, that should be at least A firstly. Otherwise, what are we doing? Again, by linearity of expectations, this will be this. In sum of indicator variables, the expected size of A naught will be summation over all V in VG, probability that V is in NT. And well, what's the probability that V is in NT? Remember, we are choosing T randomly. So probability that V is in NT is the same as probability that T is actually chosen from the neighbors of V. So what's the probability that T is chosen from the neighbors of V?
Neighbors of V upon total number of vertices.
Yes. So it's like degree of V over N raised to, okay, I'll just write mod T is T and chosen. So T is randomly chosen size subset. Okay, I have to be a little careful here. It's not, mod T is not T exact. Let me just slide digression. I have to be more careful in how T is chosen. T is chosen over small t rounds, choosing one vertex randomly per round. What we are doing is every round we are choosing one random vertex, adding it to T, choosing one random vertex, adding it to T with replacement. So it's possible that the same vertex is chosen twice, but we don't care. Like T is not what we are after. We don't care about the size of T. This is how we are choosing T. So in this case, this bound holds because every time in every round we have to choose from the neighbors of P. So the probability of that is degree V over N. So it's degree V over N raised to T. And now we use the power mean inequality. So we get, then I'll rewrite this. So this is like sum of Th powers is greater than or equal to Th power of the average. It's something like this, I think. This is from the power mean inequality, or Holder or whatever. And that is just equal to like d bar is to t bar. D bar is the average degree. It's a sum of degrees over n, which is twice the number of edges over n. But for calculation purposes, I'm writing this as d bar. So what we have got is the expected size of A naught. Okay, maybe I should not use this as A naught, but that's a bit of a. I'll just write it as NT for now. A naught is actually not this quantity exactly. So saying is the expected size of NT is at least d bar raised to t over n raised to t minus 1. And again, if we just have chosen t in this way, and what we want is that every R size subset of NT has, well, at least A plus B common neighbors. So
what if a T is smaller than R? Do we consider it as true or wrong?
what?
What if NT is smaller than R? Then do we consider it as true or wrong?
If NT is smaller than
R.
That's
I
what
mean, T
we
is smaller
don't
than R.
want, right?
Yeah.
We want T to be at least R. Yeah, that's true.
So, won't this algorithm that you're using not necessarily?
We want it to be bigger than R with good enough probability. That's what we don't want. May not be always bigger than R, but bigger than r with good enough probability, and that then will be kind of done.
Okay.
Yeah, but again, so what we want is, okay, the neighbors of T, NT, every R size subset of NT should have A plus B common neighbors. That's what we want. But we might not get that. So in fact, like, how many bad subsets are there? So that's called U, NT, bad, if mod U is R, and number of common neighbors of U is less than A plus B. So we call U in NT bad if mod U is R and number of neighbors of U is less than A plus B. The idea here is the same as what we had done for the Ramsey number. There is an alteration idea. Whenever we have a bad subset, we remove one of the vertices from. We remove one vertex from every bad subset. So what we'll be left with will have no bad subsets. So to find that.
Sir, but what if then the whatever we are left with has less than R neighbors? That seems
Less than-
probable to me.
That won't have less than R neighbor, no, because there won't be any bad subsets left.
I mean, less than R vertices.
That we in fact want to be at least A vertices, not just R, like, because our A naught will be that final quantity, right?
Yes, sorry. What if it has less than A vertices?
Yes, that's what we don't want. So we need it to have bigger than A vertices with good probability. So let's calculate how many vertices it will have on average. So firstly, let me calculate expected number of bad sets. Again, by linearity of expectation, that's the sum over all subsets of VG of size, how much is R? Now, what's the probability that U is bad? If U is a subset of NT and mod T is bigger than A plus B, so what we say is, if U is a subset of NT and mod T is at least A plus B, then U is not bad. Or like if U is not a subset of NT, then U is not bad. Because by definition, we have every bad subset is a subset of NT, right? So in fact, like, let me just, we don't even need this if here. We need an if here. So we have these two things. If mod T is at least A plus B, then U is not bad. Why? Because, well, even if U is a subset of NT, the neighbors of U will contain T, and T will have size at least A plus B. So the neighbor of U will have size at least A plus B. So if T has at least size A plus B, then U is not bad. And if U is not a subset of NT, then, like, by definition, U is not bad. So that means U is bad implies U subset of NT and mod T less than A plus B. Right? So U being bad is a subset of this event. Like, the event that U is bad is subset of the event that U is subset of NT and mod T less than A plus B.
Yeah, I got that. But you said that if mod T is greater than A plus B, then T will contain that. Like, why is that true? Like,
I said if mod T is greater than or equal to A plus B, then U is not bad. Because then NU will contain T, with U is a subset of NT.
yeah.
So every every element of T is a neighbor of every element of U. So NU will contain T.
Yes.
Just write this here. NU contains T. So if mod T is at least A plus B, we are done. That's the best case scenario. Otherwise, if U is not in NT, then U is not bad by definition. So what I'm saying is, if U is bad, then U is a subset of NT, and mod T is less than A plus B. Now remember here, what we have chosen is T. We have chosen T from this thing. So and also I'll add one more thing. That's just from definition of bad. So these three things will be satisfied if U is bad. If U is a subset of NT, T has less than A plus B neighbors, and NU is at most A plus B. So what is the probability of this? What is the probability that these three things happen if T is chosen randomly? Well, if NU is greater than A plus B, probability is 0, because U is always good. U has always A plus B neighbors. So if NU on the other hand is at most A plus B, then all of T must be chosen from NU, because U is a subset of NT. So like U must be like common neighbors of NT of T. So all of T So probability is at most NU by N whole raised to T. Right? Because if NU is small, then well, U has to be common neighbor of T. So T has to be chosen from the common neighbors of U. Otherwise, U can't be common neighbor. And so it's at most NU by T. And since we know NU is at most A plus B by N, it's at most A plus B by N whole raised to T. And well, 0 is also less than or equal to A plus B by N whole raised to T. So in the end, we get probability U is bad is at most A plus B by N whole raised to T.
Yeah, wait, but why is it not possible like that NU has some neighbor which is not a neighbor of T? Like
That's possible. Like, fine.
yeah,
But if T has at least A plus B, we are already done, because then NU is already bigger. We are finding an upper bound on this. We are not finding this exactly. All we are saying is if U is bad, then U is a subset of NT, and NU is at most A plus B. That's what I said.
yeah,
Like
yeah, I got that. But like, why should T be a subset of NU?
Because U is a subset of NT.
Yeah.
So every element of U is adjacent to all elements of T. So every element of T is a neighbor
yes.
of U.
Yeah.
That's right.
Yeah.
So is this clear then? Like this is either 0 or it's at most A plus B by N raised to T. So we just give a very rough upper bound. This is always. And we had a summation over all subsets of VG of size R. So in the end, we get expected number of bad subsets is at most N choose R into A plus B by N raised to T. And what we are going to do, we have this NT, and from NT we are deleting one vertex each for every bad subset. So how many vertices are we deleting? At most these many, on average. And we are looking at A0 is NT minus like one vertex each for bad. This is how we define our A naught. And so the expected value of A naught, again we use linearity, is just expectation of NT minus expected number of bad. Right?
Yeah.
And
like T was picked in rounds, right?
huh?
Like how was T picked? It was like in T small T rounds.
T was picked in small T rounds. Every round we are picking one
Yes.
vertex randomly. And well, we have a lower bound on this. This is at least, the first term is at least d bar by t raised to n minus n raised to t minus 1. And the second one is at most this. So if we take the minus, we get all we need this above quantity to be greater than or equal to A. Then we'll be done. But again, the expectation of A naught is at least A. That means for some value of A naught, it will be at least A. And we'll be done. And so we do a similar thing as what we had done before. We are assume ki let's say number of edges, we want a bound of the form C times n raised to 2 minus 1 by R, right? So that means D bar is, okay, I think everything below this got deleted for some reason. But anyway, I'll write the final bound. We had gotten this d bar raised to t upon n raised to t minus 1. We want this to be greater than or equal to A. And so, well, what we choose the number of edges. The bound that we finally want is some C n raised to 2 minus 1 by R. And so that would imply that d bar is some C into 2C into n raised to 1 minus 1 by R. We'll put this in the above quantity and simplify slightly. And we choose t equal to R. Now, we have not chosen small t yet, but if you do some optimizations, we see that t equal to R is in fact like the best quantity. And we use the bound that n choose R is at most n raised to R by R factorial. That will give you a lower bound. If you put this all, you will get that we need 2C raised to R minus A plus B raised to R by R factorial. We want this to be at least A. So we can take C to be greater than and this is independent of n.
All of this over 2, right?
Huh?
Like 2
C
to
should
the
be
R.
greater than all of this over 2 because it's 2C to the power of R.
Yeah. In fact, if you take like even if you remove the 2, like, that will still be true.
Yeah, right. It doesn't change anything.
Yes. So in fact, you can take C exactly equal to that quantity. Like you can take C exactly equal to this quantity, and that will work. So yeah, I think Shreyan had asked me what's the value of C. This is the value of C that works in terms of A, B, and R. I think it's roughly a pretty small value actually. It's like roughly A plus B, roughly like A plus B by R, I think. So yeah, in fact, a very small constant, linear in number of vertices. So yeah, that's how this final thing that we did. So that there were three maxims that we used. First is like choose randomly. Second one is alteration is important. And third one is dependent choice. Where did we use dependent choice here? Well, we didn't choose A directly, A naught. We chose A naught and A naught dependent on something we chose randomly. So we chose T randomly and we constructed A naught in this complicated way. That has gone for some reason now. But yeah, that's where this paradigm comes into play. You don't choose what you want directly. Look at the properties of A naught. What properties do we want? And on that basis, you choose something else randomly and choose A naught according to your needs. Right, so, any doubts in this part? Question? For some reason, like everything below this has gone.
Wait, could you just write the final result?
Yeah. Oh, yeah. That is, I've written it. Did I not write it? Okay, I've not written it. Okay.
Yeah.
The final result is key if H is bipartite. I'll just write it as A union B comma E. Every vertex in B has degree at most R. Then X in H is co-H in raised to 2 minus 1 by R. This is what we proved, fine. In fact, we found the constant as well. It's roughly the K plus B by R.
Yeah. And like there we were choosing, like we chose D bar to be 2C n raised to the power 1 minus 1 over S, right? Like why did we choose that just because we wanted to prove the result?
I chose that to save time. I mean, ideally, what we want to do is we want to estimate this D bar. Like we have this inequality for D bar, right? D is at least this much. We can choose T equal to R because, okay, let me just do the calculation slightly helpful. So we have D bar raised to T upon N raised to T minus 1 minus N raised to R by R factorial. This is N choose R into A plus B raised to T upon N raised to T. And we want this to be at least A. This is what we want to solve. And we want to get D bar somehow.
Yeah.
Now, we want like no dependence on N. So it makes sense to choose R equal to T. Because then this term will get cancelled.
Yes. But there
Right?
will yes. Oh right. But then there's also another n down below D bar.
So that's fine. But like this term gets cancelled. So what we want is D bar raised to T upon N raised to T minus 1 is at least A plus this quantity A plus B all raised to R by R factorial, which I'll call C from now on. So what we want is D bar raised to T is at least C into N raised to T minus, maybe C naught into N raised to T minus 1. So we want D bar is at least C naught raised to 1 by T. This is also some C1, let's say, because this R actually, R. T is equal to R into N raised to 1 minus 1 by R.
Right. And then take
Number of. This is just this times N, so this is C2. This is what we get.
Yeah, that makes more sense.
Yeah. That concludes that. Any other doubt? Okay. The very cutting edge result that does not use very. So I have not mentioned the max probability that we have used is like linearity of expectation. I have not mentioned any Markov inequality, Chebyshev inequality. I think this is like the most cutting edge you can go without using any advanced probability. Not in advance, but without it using. After 2003, I think all results use some.
Wait, do you have this paper like in which this was published?
I
did some Google searching and I think I found it.
Like could you share it on like
I
Discord or
think it should be
TL?
titled Turan numbers of bipartite graphs and related Ramsey type questions, right?
I
Okay,
have
wait,
no
like
idea. Like I've learned it I have the notes for this from my course. So
Okay, I'll just put the
I'll
link.
put that in the description.
yeah,
It's in the Zoom chat and I'm also putting it in the Discord server.
yeah, thanks.
This is Sudoku. Yeah, I think this is. You can go through this paper. I think. Okay, but the way Alan writes, all of his papers are written in a reverse fashion where he gives some random lemma in the beginning,
Yeah.
and then he's and there are like other results in that paper as well. Actually, which are interesting. All these
Yes.
publishing. You can go through that one. Yeah. I wanted to cover something that's not generally covered in probabilistic when you're first lecture of probabilistic. Yeah, any other doubts and questions? Okay, great. I think we can end now. Stop sharing.
Thank you so much. This was
Yes.
really nice.
Yes.
Thank you.
That is